Okay, so today I'm introducing the height of the commons lab, and we're actually going to take the measurements tomorrow. But I thought it would be a good place to talk about law of cosines and law of sines because we've got another not right triangle. So here, the kids saw in class that I sighted up to the clock on the wall, and I used an app on my phone called Measure, and we used the level within that. And then I was able to see that it was an 11-degree angle the first time I sighted up to the clock. Then I walked 6 feet forward. This is important. That distance was 6. And then I took a new angle. And the new angle of, what's that angle of what? What's it called officially? Angle of elevation. The next angle of elevation moved to 20 degrees after I moved forward 6 feet. Now, I could have just walked all the way up to the wall, and then there wouldn't have been any issue of, like, they would have been super simple. Do you get if I told you this whole distance and I said it was like 18? That would make the problem incredibly simple. How tall is the clock? Okay, and that there's nothing wrong with that. But sometimes you can't walk all the way up to the thing. Like, for example, let's say that it is a skyscraper, and you are in Chicago, is one place where there's a lot of good skyscrapers, and you're trying to figure out how tall a skyscraper is. Do you get that the skyscraper could be a quarter mile away from you when you're doing these measurements? And maybe you don't want to have to walk and measure how far a quarter mile is. That's like, over 1,000 was, I don't know exactly what it is, 5,280 divided by 4. But anyway, it's a fairly long ways. Maybe you don't want to walk that far. So you walk part of it and go, okay, I went 100 feet, take a new measurement. You see what I'm saying? This could be handy because you don't have to walk all the way up to the thing. Now remember, when you're done, you'll be finding this distance. Is that actually the height of the clock off the ground? No. What do we have to factor in to get it to be the height off the ground? My height. And we're going to say that the height of my eyeballs, like right here, is 5 feet, just to make it simple. Okay, so my question for you is, find x and find y. But really, all I need is y, because that's what the height of the commons is like. It's how tall is the commons. And we make it a strange way. I'll show you later exactly how we want you to find the height of the commons. There's a super easy way, and it is walk all the way up to the wall and get this angle here, and let's say it's a 40-degree angle, and then to get this whole distance here, let's say it's like, 81 feet or whatever, then you can figure out how tall the commons is with a simple right triangle. Nothing wrong with that. But the height of the commons lab makes you do it in a more complicated way, kind of like this. All right. So next, there's equations that you can use and stuff, but a lot of people find that this new technique of using this pink triangle is kind of handy. You can find all the sides of the pink triangle? You didn't used to be able to, but now you can with just one simple equation. It's called the law of sines. All right, so I've got a side, and let's figure out the angle across from it. All right, would you agree that this angle right here, that angle is 160 degrees? And if I know that that's 160 and the other one's 11, then I know this angle. What is that angle up there? 8 degrees. No, 9 degrees, right? I thought I heard somebody say 8, but was it 9? Is it 9? Okay, because I allowed it to 180, right? Okay, so now I got my 3 angles and I got one side. Do you get that you can use law of sines to figure out this side right here? Let's call it H for hypotenuse. Do you get what I'm saying? I can find H by using law of sines. And once I've got that, and I got a side and an angle in a right triangle, I'll make it the blue bar triangle right here. Then I'll have a right triangle with a side and an angle, and then it should be pretty easy. But see how that one extra little step of using the law of sines can be pretty handy? All right. I would like you to, I'm going to give you a partner for today. Problems are going to get hard. You'll be happy to have one. Pausing for a second. Okay, so now that you're with a partner, solve for h and then solve for x and y. You'll need a calculator. If you haven't already got one out, get one. If you need to borrow one, come up and ask. So let's see if you learned how to use the law of sines properly. Sine of an angle, which in this case I am going to use, well, I want the angle where I also have a side across from it. That would be the 6 and the 9. So sine of 9 over 6. Raise your hand if you set that up properly. Okay, good. And then I can do sine of the other angle, which, well, let's go with 11 over, I don't know h, so I'm going to solve for h. There we go. And now I'm going to pause for a second while I grind out the math on that, which is sine of 9 is some decimal. I'm going to divide that by 6. And then I am going to take all of that and take sine 11 divided by that. Anybody verify 7.3? All right, awesome. At the end, you did an inverse. Oh, you didn't do an inverse. Sorry. You just cross-multiplied and solved this thing out. I need to know the decimal more clearly. 7 what? 0.32? All right. All right. So if that's 7.32, then the rest of it should fall pretty quickly, because I can do sine of 20 equals y over 7.32, and cross multiply and solve that. And then what is y? Just y, not the 5 foot extra, just y. 2.5? Can anybody verify 2.5? Okay. Then 2.5 plus my height makes the clock actually 7.5 feet. And if I am about, well, my eyes are about 5 feet, does it seem possible that that's about 7.5 feet? Okay. It might be more like 8, but it all depends on where I aim to on the clock. Did I aim to the bottom or the middle? And do you get that I wasn't super accurate on measuring? You know what I mean? My angles weren't perfect. My distance wasn't exactly perfect. So if I'm within a foot, that's not bad. Same thing on the height of the commons. I am not going to expect you to get the height of the commons exactly, because I know your measurements are going to be off a little bit. One thing that helps, there are tiles in here. Do you see? Look down at the floor. They are 1 foot by 1 foot. Do you see those? And they don't have any gaps between them, which is really nice. So they're all 1 foot, and so therefore, if you look at and count how many blocks there are on the floor, that's exactly how many feet it is. There's something like that out in the commons. The only sad part is they're not exactly 1 foot. But then when you add the grout that goes around those, there's fairly wide grout out there to make it look nice. They basically, including the grout, they're about a foot. And again, we can be off a little bit, so it's okay. All right, so you're going to be measuring out there using the squares, the boxes, the tiles that are about a foot by a foot. Okay. I did measure over the course of 4 feet. It might be off an inch or 2. So, you know, you're going to be off a few inches, but that's okay, because we're going to give you a wide range that's all right. So imagine for a moment that this is a spot up at the very, you see over on the right side of the screen there, I put a dot. That's a spot on the ceiling of the commons. Do you get that this is a way you could have done it, where you sighted up to it with your phone, figured out an angle, you walk closer, sight up to it again, and you just need to know how far you walked in between here and here. And that's what we just did. That wasn't that hard, right? Okay. Then, what's another way? Well, the easiest way. What's the easiest way to find the height of the commons? You just walk all the way over there. So you get this angle right here, and you figure out that it's, you know, let's say it's 35 degrees or whatever, and then you just walk all the way over here and measure exactly how far that is. But what if the tiles don't reach all the way? You see what I mean? That could be a pain. You might run out of, like, I could walk all the way to here, but then what am I going to guess the last, you know, and say that's about 10 feet? I mean, if you want to estimate, sure, you could do that. But, all right, so how are we going to find the height of the commons? We need a sky view now for height of the commons. Okay, so now this is us looking down on the commons from up on the ceiling. Okay, you got to imagine yourself up there looking down. You know how there's those little circular tables along the side of one part of the commons? You know what I'm talking about? Down here, there's some like planters. If you go way down the commons down there, there's like some planters with trees in them. They still have trees in them? I think they do. Okay. They're hard to keep alive on the inside of the building like that. All right. So we're looking down onto the floor of the commons. Imagine somebody right here, standing right here. We're looking down at the top of their head. Okay. And they are looking straight this way. Do you get, if they were to walk that distance and know that it's 35 feet, and then look up at the ceiling and get that angle measure, they're going to have the height of the commons really quick. That is a way to do it, and it's okay. But if the area you're in doesn't have squares all the way, maybe you'll want to do it this way, where you have, I know this is like 10 feet, and you take two angle measures and use your 10 feet like we just did. That's one way, and you can do it any way you want for one of your ways for finding the height of the commons. But here's the other part that you have to do, because this is the hard part of the lab. The hard part of the lab is if you are looking straight forward and there's a spot on the, now this is on the ceiling. Imagine that you're looking up at the ceiling. I can't do this in 3D. I'm going to sort of say this was looking up at the ceiling. Okay. You are going to walk this way at least 10 feet. I'm going to recommend 10 feet, okay, because it's a nice round number. And then you're going to go look up at the commons again. You're going to look up at the same spot you looked at in the first place, which is now kind of over that way. And you've gotten farther away from the spot on the ceiling, so that angle will get smaller. So let's say your angle was 65 degrees. And now it gets smaller, and now the angle is only 60 degrees. Now you can find the height of the commons. All right, here's another teacher's attempt at the 3D on this. Okay, and I think it's better than mine was. So here's the person from their eyes looking up, and they get the height of the commons, and then they move 10 feet over, and then they sight it up there again and get the height of the commons again. So you're going to get an angle in one spot. Let's say this was 60 degrees. And when you get further away from the spot on the ceiling, you are going to take another angle measurement, and it will be smaller, like 55 degrees. And then you can figure out the height of the commons. Now, I'm purposely not showing you exactly how to do it. This is a lab. You're supposed to, that's the part you're supposed to figure out. And why would you ever do it that way? Well, what if you're standing in front of a lake and you see a building across the lake? I'll give you an example. The Carlson Towers. You can see them from Lake Minnetonka. There's a little island on Lake Minnetonka where you can stand and you can look up and see the Carlson Towers off in the distance. Okay? And you get an angle measurement on the Carlson Towers. But you can't, well, maybe you can, but you don't want to walk out into the lake a long ways and take another sighting. Okay? You'd rather walk down the shore of the island, and so you walk, again, laterally. You walk at a 90-degree angle to your first sighting, and you walk this way a long ways, and then you take another angle measurement. All right, one last thing that's going to help a lot is the law of sines, and then also, what do you think the other one is? The law of cosines. And it's almost like you're getting an advantage because I waited on the lab. Because you didn't used to know the law of sines and law of cosines, but now I can't stop you from using knowledge, right? Like, I can't say, don't use that part of your brain that learned the law of cosines. Okay, so you're allowed to use the law of cosines and law of sines to answer this question. But you can't just do it the easy way, which is to walk all the way up to the wall and get that distance, 100 feet here, and then find this angle is like 30 degrees here. That's just too easy. Although, it's totally okay to do it as one of your two ways where you find the height of the commons. Okay, so you'll know what the height of the commons is pretty well from that easy way. And then you can do the other way and see if you can get the same answer to come up. Will it be off a little bit? Yes, because we have angle issues. Like our calculator, or sorry, our cell phones that are giving us the angles aren't perfect. And kids hold these in different ways. And one person holding it up, might get an angle of, hold on just a second here. Sorry, issues. There we go. I'm holding up the app called Measure on my phone. And what kid might hold this? And I don't know. Can you read it for me? What am I getting? 13. And another kid doesn't really understand how this works and like tilts it like that. Is that good? You know, do you see what I'm saying? It totally changes the angle. Okay, you might want to get a second opinion on your angles. Like you measure it, have your partner. You can have a partner for this lab. Your partner measures it too. Okay, and you both stand here and look at it, and maybe one of you is holding it all goofy, and it's, you know, you can talk to each other about getting the right angle. All right, so there's angle issues, and there's also distance issues. The blocks, they are 1 foot each, about, but they're not perfect. So if your height of the common comes out slightly different than each other, it's okay. All right, we will actually go out and measure that tomorrow, but then the key to that will be, if you take a measurement right here, you need to be looking straight at like a, you know, nice straight angle across. Here's the sides of the commons, at the ceiling, at a spot right where the ceiling meets the wall. And then you're going to walk at a 90-degree angle here and record, hopefully it's 10 feet to keep your life simple. And do it again to the same spot on the ceiling. You don't change spots on the ceiling. You're measuring the same spot. That's why the angle changes over here, and it should be a little smaller than the first time you looked up at the ceiling. Okay, enough about that. Back to law of sines and law of cosines. When would you ever need the law of cosines? I'll give you an example. Law of cosines is when you have an angle and the two sides around it. That's a pretty slick time for the law of cosines to come in. And what can it tell you? Every other angle and every other side in the triangle. Well, this is a triangle. I've already given you two sides, so there's only one side left, and then there's two angles that it can figure out. Okay? What is the law of cosines? It's kind of like a right triangle, a squared plus b squared equals c squared, but I'm leaving a whole bunch of room in here. Because why? Does anybody have it memorized? A squared plus b squared, and then there's this little extra factor thrown in, and then it all equals c squared. All right, write this down. This is the law of cosines. Minus 2ab, using smaller, lowercase letters, 2ab cosine of big C. I'm using the file. It hasn't crashed so far. Thank you. So far. Okay, so notice there's only one big angle in there. That big C, that capital C, that's the only angle. All the rest, those little A's, B's, and C's, those are all sides. So you might be like, but I don't know all the sides. Right. That's the point. We'll help you figure out the other side. And what side do you think we should figure out? You see how it's already solved for C? So you want to call the side you want to solve C. Okay? Notice, I don't care which, the 7 or the 8 are A and B. It doesn't matter what I call those. But the one side I don't have, this black side here, I'm going to call that C. Why doesn't it matter which ones A and B are? Look, if I put A here and B here, do you get, I'm just going to square them and add them. So it doesn't matter whether B was A or A was B. And same thing here, I'm going to just multiply A and B right next to each other. Would it matter if it was 8 times 7 or 7 times 8? No, we don't care about A and B. So do we not care about any of the sides? I didn't say that. The one side we have to care about is the side we're trying to solve for has to be C. All right, so now if that's C, can I pick this to be A so that means this is little a? Sure. And I can pick this to be B. Wait a minute, B's up here, so that this is little b? Sure. You can do that, and then that makes this has to be big C. But it didn't matter whether you call this A or this B, it didn't matter. Okay. I'm going to label it this way just so you have something to go from. And I'd like you to figure out side C. Remember at the end, it's a really big number. Then you got to take the square root of it to get C alone. All right, I'm going to pause for a second while you do your first calculation using the law of cosines. Okay, you can take a look up here and see if you're getting the same things as me. 7 squared plus 8 squared minus 2 times 7 times 8, cosine of 30. Now, at some point, I should figure out cosine of 30, so I'm going to do that. Cosine of 30. Make sure I'm in degree mode. I am. and it's 0.87 or 0.866. If I use 0.866, it'll give me a slightly more accurate answer because I get 3 decimal places. So, all right. Go ahead, solve this down the whole rest of the way. At the end, you got to remember the square root. Pausing for a second while we do that. Can anybody verify they got down to about 16 equals c squared, which means that c must be about what? 4. Now, if you're like, wait a minute, Mr. Server, there's a plus and a minus. In this case, the negative side would be extraneous because you can't have a side that's negative, okay? So anyway, technically it would be 4 and negative 4, about. So that's about 4. Is it exactly 4? No, it's really, really, really close to 4, though. Raise your hand if you were successful on that. Okay, good. Now that I've got that, you could use the law of cosines again to find angle B, but what would be smarter? Law of sines. It's so much easier. It's got 4 numbers, and they're all set up in little proportion. It's so much easier than the law of cosines. So law of cosines is handy, but when you have a choice, usually after you've done the law of cosines once, you have an angle and a side across from it, so then you should start using the law of sines again. Work with your partner to figure out angle B, and then angle A will just fall into place because they have to add up to 180 because they're a triangle, right? So everybody find angle B using the law of sines. Law of sines. Law of sines again, sine of an angle. Well, we only have one angle, so better use 30. Over the side across from it, which is 4. We just figured that out. It rounded to 4. Equals, and then which one do we want? Sine of B. But I don't know B, so you put a B. And then we'll solve it because we got the side across from it, which is 8. And sine of 30 is a half. Ooh, that's slick. And then I'm going to multiply both sides by 8. And that'll be really handy. Let me show you why. Timesing by 8 on both sides. That cancels that. And 8 times a half is 4. And 4 divided by 4 is 1. 1 equals sine of B. And then you do inverse sine of 1. And what did you get? 90. Weird. Do you get, if this is 90 degrees, do you get it kind of almost looks like a 90? If it was exactly a 90, then this would have been a 30, 60, 90 triangle. And it's just that these two have been reversed. It's not exactly 90. You know why it's not exactly 90? Because this wasn't exactly 4. But if by rounding it, it ended up making it look like our 30, 60, 90 was wrong since the beginning. All right. Okay, so that's the law of cosines. Just to sum it all up, would everybody please try to solve this question because it uses the law of cosines. Would you agree that the 3, 4, 5 triangle is a thing and it's a right triangle? But did you know there was a 3, 4, 6 triangle? There is. But it's just not a right triangle. There is not a 1, 2, 8 triangle. It doesn't exist, actually. Try to figure. John is like, nope. Okay. Anyway, would you please figure out that angle right there? And since it's the one I want, I'm going to use C. Remember that the law of cosines, the thing you're solving for should be C. It should either be angle C or side C. The only letter that's important is C. A and B can be anything, but C should be the one you're solving for. So if I'm solving for that, I'm calling it C. Yep, and you can call them A and B, and it doesn't matter which one's which. But the one you're solving for, we call C. All right, go ahead and use the law of cosines, because hint, law of sines couldn't possibly work. You don't have any angles. No way to do it. Law of cosines would work, though. All right, I'm going to pause for a second. Let me give this a try. Okay, I'm going to get started. It's a squared plus b squared minus 2ab cosine of big C And A and B don't matter. So I'm going to call this A and this one B, but if you used it others, it won't hurt. It'll be fine. So that makes this 3 squared plus 4 squared minus 2 times 3 times 4 times cosine of big C. I don't know big C. I know little c, and that's 6. Sometimes people ask, why is pre-calc so hard? Because the easy part of this was solving that equation. Know what I mean? Like you end up with like a 9-step equation to solve after you've figured out what's going on. Okay, so that's one of the reasons that pre-calc is so hard. There's so many steps. All right, at the end it was inverse cosine of negative 11/24. I'm going to give that a try. If you see a mistake, please tell me now. Because I do make mistakes. You've seen that. Did you get 117? Raise your hand if you did. Awesome. 117.24 was my angle C. Make sure I rounded that properly. I'm wrong. 117.28. Sorry about that. There we go. Yay. Now that I have that angle, I've got 2 angles, and therefore I could well, I'm wrong. I only have one angle, 117.28. I could find the other angles, though, because I've got a side and an angle across from it, and that's perfect for law of sines. Don't have to do it, though, but I think you get the idea. Law of cosines is almost always followed up with, and now use the law of sines to finish the problem. Okay. All right. So your homework for tonight. It has that annoying problem of some of these answers aren't possible. Okay, I'm going to talk you through that. Everybody find the first question. It's okay. It happens on tests too, where the answer is that there is no answer. There's no solution. All right, here. Did you find that slide? All right, so I'm going to draw a little triangle with an angle of 117. Do I know exactly how big 117 is? No, but I know it's bigger than a 90, right? And it's alpha, which is like a capital A. I like to do it that way. And this is 35. And if that's 35, which one's going to be 42? Help me think this through. You're shaking your head. What do you think? I don't think there's a solution. I agree with you 1,000%. There is no solution. Because if that's really 35, how could one of these sides be 42? It would have to have an angle that's even bigger than it. See, that gave me a 35. That means the biggest angle in the triangle has to be the 117. You can't have another big angle like that. You can't have 2 angles that are more than 90 in a triangle. That's not possible. So that means all the other sides have to be smaller than 35. Do you get what I just said? If you got that, then you'd be able to just on the test go, oh, no solution on this one. No solution because, and you'd have to be able to explain why there's no solution. It's too easy to just go, I'm stuck. I'll say no solution. You have to be able to say no solution because this side would have to be smaller than the 35. Okay, so there's your first problem. Then we're doing this one, and this one works. And what's the point of these? Just drawing them? No, you got to find all the other angles and all the other sides. So this has 2 of the sides. That leaves one side left to find. And then you got to find the other 2 angles. you guys not talk as much, please? Thank you. All right, so these two are assigned. These two are assigned. And that one more bearing question, and that brings up a good point. Bearing, if you got it already, you know, the compass rose thing, then awesome, because you're having that again. There'll be another test with bearing on it, at least one more. For those that didn't get it the first time, don't just like, well, okay, I didn't get too well on that test, but no, you got to get this down. It's going to happen again. And it'll be on the final. But if you're not good at it, you can console yourself with this. I just checked with a calculus teacher, and they said that they do not have bearing in calculus. So if you want Calc AB and Calc BC, there's no bearing. You do get it again in Calc 3, but not for the next couple of years. So if you're not good at bearing, just don't try to like tell people directions on how to get home using a compass, because that's what you really are using. That's bearings. If you understand it, that's about getting you home with a compass. And thankfully, most of you have GPS, and you'll be fine. Okay. And again, vast majority of you figured this out, which is awesome. Just trying to say, don't think, wait a minute, that's last chapter. It's just a review question. Nope. It's going to be on the next test again. Okay, so that's all I have for you for today. I have one just food for thought kind of question, because I know this is important. It's going to come up on a major test sometime soon. If I gave you this angle is 30 and this side is 8, does it seem possible that this side here could be 6? Does that seem possible? Okay, I hope it seems possible, because it is possible. But a lot of times kids will realize, wait a minute, that last side of 6, it could have been out that way and also been 6. Do you see what I'm saying? That triangle, if it has sides of 8 and 6, and this angle's 30, there's two ways that that 6 could have been. It could have been swinging out, or it could have been swinging in. That's called ambiguous. Ambiguous means you can't tell for sure. Okay, so there is a problem like this. So how would you do it? Well, you can actually use the law of cosines to do it, or even the law of sines. In fact, the law of sines is easier. You got a side and the angle across from it. Do you see what I'm saying? So when you do this, what you do is you always do the triangle that involves a smaller angle. Do you get the blue one here compared to the red one here? That this one's smaller? Because at the end, you'll understand this later. You can even come back and listen to this video a month from now, and you'll go, oh, because I'm doing an inverse sine. We have a whole test on inverses. Because I'm doing an inverse sine to solve the problem, the answer for any inverse sine is always less than 90. So at the end, kids solve this, and if they drew the triangle like this, they are baffled when the angle comes out to 41 degrees. And they're like, but it's bigger than 90. But actually, this is 41 degrees. And therefore, this is 41 degrees. And then you can figure out what that one is. So the moral of the story is there are triangles that sometimes are hard to draw and ambiguous. And when you solve them, if you get an answer that just doesn't make sense, draw the two options out. And what you will always be finding is you'll be finding the smaller. If your answers were either this or this, you'll be finding the smaller of the two. And that's called the ambiguous case. It's just a quick overview. We'll do another one of those for reals tomorrow. All right, sorry I had to talk over some of your homework time there, but the rest of the time is yours.